Okay, welcome everyone. Thank you for joining us for another virtual Center for Machine Learning seminar. I'm very happy today to welcome Ruiqi Gao. So Ruiqi received her bachelor's degree from Peking University and then a PhD in statistics from UC Los Angeles. She graduated last year. And since graduation has moved on to become a research scientist at Google Brain. And so she's done a lot of really interesting work on deep generative models with applications to things like representation learning. In particular, she's focused on a type of deep generative model called an energy-based model. And she's going to tell us a bit more about this work today. So Ruiqi, please go ahead.
Okay, yeah, thank you, Eric, for the introduction. Yeah, hi everyone, I'm Ruiqi, and I'm very glad to be here to make a presentation on a type of generative models I'm very interested in. It's called energy-based models. And today I will talk about some advanced training algorithms of energy-based models. So in the past few years, we have seen amazing progress in generative models that are able to capture the structure of complex data sets. And these models open up new capabilities for machine learning systems. However, existing methods often exhibit trade-offs between speed of sampling, quality of generations, diversity of samples, and training stabilities. So for example, recent advances in the language domain have largely been powered by the autoregressive generative models, as shown in the top right figure, that generate sequences one token at a time. So for images, it's just like generate one pixel at a time. While these models are fast to train and scale well, generation is like sequential and could be slow for like long sequence or large scale images. And you also need to know an appropriate order of generation when dealing with this type of models. And on the other hand, the latent variable models like GANS, VAEs, or normalizing flows are able to produce samples much more rapidly by directly transforming a noisy latent variable into a structure output. But either they exhibit like training instabilities or poor diversity of samples like in GANS, or like poor sampling qualities as in VAEs or normalizing flows. So finally, the energy-based models originated from statistical physics present an alternative way of constructing a generative model that captures the dependencies by associating an anomalized probability energy to each configuration of the input variables. So samples can be generated by iterative MCMC sampling from the fitting model, as shown in the bottom right figure. And previous work has shown that energy-based models are stable to train, but requires MCMC sampling during training, which is prohibitively expensive. And the sampling chains may have difficulty to converge and mix, and thus results in poor sample qualities and biased models. So in this talk, I will present two work to address these issues with energy-based models for images and show that the energy-based model can actually be trained efficiently, produce high sample quality, and can be applied for downstream tasks such as representation learning. So first, let's look at what are energy-based models. So the energy-based models can be traced back to the Gibbs distribution in statistical mechanics, which defines the probability of a system like will be in a certain state. For example, the left figure is the Ising model, which is designed for models for modeling the ferromechanism. And examples in Bayesian network include the Markov random field in the middle figure, where the dependencies of variables are captured by an undirected graph, and the scalar energy is defined based on this graph. And in recent deep learning literature, the energy is simply defined by a deep neural network, which takes a high dimensional signal as input, such as an image, and output a scalar value. So to be more specific, an energy-based model parameterizes a density only using its unnormalized log density function, which is this f theta x. so that P theta x is in the form of exponential f theta x divided by d zeta. And sometimes people use this negative e theta x, where this e theta is the energy. So here, this f theta or this negative e theta can be, theoretically speaking, they are almost free form, meaning that they can almost be any function that learns a mapping from a d-dimensional data space to a scalar. And this d theta, sometimes it is also called partition function in statistical physics. It is usually analytically intractable because this integration operation, especially on high dimensional data space. So the energy-based model also belongs to the unnormalized probabilistic models because we cannot get the normalized density out of this model in closed form. Okay, so why do we prefer these energy-based models compared to the other type of generative models? So it has the following potential advantages. So first, the energy-based model, like the f theta x, is the only object that we need to design and to train. So it is simple and usually stable to train compared to the GAN models and VAE models, which need some auxiliary network to jointly train. And second, the energy-based model can be viewed as a generative versions of discriminative models due to the following correspondence. So specifically, suppose we have k categories, and suppose for each category we have a p theta k, which is the model for that specific class. And this p theta k is parameterized by an energy-based model. Then by simply applying Bayesian rule, we can derive the posterior distribution of the label k, even the input x, is in this formulation. This is like exactly our commonly used softmax classifier for discriminative learning. So the energy-based model actually provides a natural way to unify the discriminative and generative learning. And because this f theta, we can use any existing discriminative architecture to parameterize it. So this energy-based model can serve as a natural feature extractor for representation learning, and it can be learned from unlabeled data. And third, the fact that this f theta can be nearly free-form makes it easy to apply the energy-based models to different domains parameterized by different model architecture, such as the graph neural network or some specific architecture design for protein, for text, or for 3D data. And lastly, since the generation process is implicitly defined and guided by the energy function or guided by the probability distribution, so it is easy to adapt a learned energy-based model for various conditional generation tasks without retraining or fine-tuning the model, as I will show later in one of the work. Examples include inpainting, super resolution, domain transfer, and many more like different tasks. Okay, so the main difficulty of like energy-based model is the training. So the training process of the energy-based model can be illustrated by these two figures. So suppose this colored map is the energy landscape defined by the negative the energy function Ex. Then the training process of the energy-based models is to put the observations in our observed dataset to the regions of low energy. While for all the other inputs or samples, we put them to the regions of high energy. And this is another 1D illustration. So suppose this curve is the energy landscape, and after training, we want to put all those observed samples to the local modes of this energy landscape. Okay. Please feel free to interrupt me if you have any question. Okay. And so now let's look at the specific formulation of the training of energy-based models. So recall that we cannot compute the probabilities for the likelihoods in a closed form due to the intractable normalizing constant. right? So we cannot easily train them by simply maximizing the log likelihoods. So we need to be a little bit more clever. So what we can do is like, we notice that although the log likelihood is not in a very nice form under this model, so the derivative of the log likelihood, which is also the derivative of this negative KL divergence between the data distribution and the model distribution. So this term could be written more simply as the difference between the expected derivative of this negative NG function evaluated at the data density and the model density. So by using this observation, we can use this equation to estimate the gradient and then apply any gradient-based optimization approach. Okay, so this looks like a surrogate objective where we use data samples, which are those blue points, to tell us where to push up the model in terms of likelihoods. And then we draw samples from the current model, and we use the samples from the current model, which are those orange points, to tell us where to push down the current model with respect to the likelihoods. So by following this approach, we can finally put these two distributions together. So this approach is also referred to as learning by synthesis, because for learning, we need to draw samples from the current model, which is this p theta. Okay, so unfortunately, again, because we don't have the normalized density, we cannot draw the samples explicitly. We have to resort to MCMC sampling techniques to draw from the current model, this p theta. And this MCMC could be extremely expensive on high dimensional space, because like for high dimensional data distribution, for example, an image data set, it is likely that like the data distribution is highly multimodal, so that the current model could also be highly multimodal, which could make the MCMC have a difficult time to traverse different modes and take a long time to converge or mix. So this is the main bottleneck for training NG-based models on high-dimensional data space. So in recent literature, a commonly used gradient-based sampler is this Langevin dynamics. So it could be easily understood as, you can see like this X is the current sample, and this term amounts to a gradient ascent of the current sample along the direction of increasing the probability of the current sample, and plus a diffusion term or a Brownian motion term. So this term has an effect to help the sampling chain to jump out of the current local mode so that it could explore different local modes along the sampling chain. Okay, so to tackle this bottleneck, people have applied these short-term MCMC techniques in the literature to train NG-based models. So the idea is like, during training at each iteration, we just run a fixed number of sampling steps initialized from white noise signal. And several work have shown that using this technique, we can generate realistic samples with the same amount of fixed number of sampling steps after we train the model. Unfortunately, an observation is like, with such small amount of MCMC sampling during training, the sampling is actually not converging or mixing. So what's the problem of non-convergent MCMC through training? So let's see some diagnosis. So we could observe that after training, not even long-range sampling chains still remain realistic. So what does that mean? So suppose during training, at each iteration, we run 100 sampling steps. Then after training, if we still run 100 sampling steps, which is the middle spectrum of this figure, then the images still remain realistic. However, if we continue to run more sampling steps, for example, 1,000 or even 10,000, hundreds of thousands sampling steps, then the images would become oversaturated and they are not realistic anymore. And if we look at the learned model or the estimated density, the situation could be even worse, as shown in the bottom left figure. So suppose these are two simple 2D examples, right? And after training with the short-term MCMC, the samples could look reasonable if we still use the same amount of sampling steps after, in testing. However, the learned density could be much far away from the ground truth data density, and it is not faithful, so that we cannot use the learned model to evaluate the learned potentials on testing data, or apply the learned model to relevant downstream tasks, such as out of distribution detection or representation learning, because the model itself is malformed, although we might be able to generate good samples from the model. So if we look at the reason of this issue more closely, so let's look at this figure. So suppose this this black curve is the energy landscape of the current model. And then during training, because the MCMC is not converging, so the samples we draw through training, as illustrated by this orange curve, it does not go to the local mode of the current model. Instead, it just stands on the halfway up the mountain. So for example, at this position. So when we try to match the data distribution and the model distribution through training, the realistic images or realistic samples would also reside on this halfway up the mountain instead of in these local modes. So after training, if you still run the same amount of sampling steps, you can still reach this halfway. However, your learned model can be far away from the true data distribution, which still on this halfway. So that is the reason of these strange observations. Okay, so after having those observations, let's look at the spectrum of MCMC sampling. So if we really care about learning a valid model instead of just learning a good sampler, so we wish we could simply just run, like, for example, 100,000 sampling steps during training per iteration, so that the MCMC chains fully converge and mix, which might solve most of the issues I have covered in the previous slide. However, given the current hardware, we can afford maybe just as many as 1,000 sampling steps, or maybe even less sampling steps through training. And compared to the sampling steps we need to make sure that the MCMC's chains would converge, still like 2 orders of magnitude in efficiency are missing. So that is the main issue we want to resolve in this talk. That is how to get rid of this computational bottleneck of sampling when training the energy-based models. Okay, so the first method I want to talk about is called diffusion recovery likelihood. So in this work, we want to answer a question. So given the fact that for a high-dimensional data space, for example, on this image space, the marginal distribution or the marginal energy landscape is pretty complicated, so that the MCMC may take a long time to converge. Can we find a way to simplify the energy so that the MCMC could become easier? But at the same time, we also don't want to constrain the expressivity of the model itself. So the answer we provide here is that, okay, so instead of directly learning the marginal distribution, we can try to switch our attention from the marginal distribution to a type of conditional distribution defined as follows. So given a clean image X, we assume like the marginal distribution of this X is given by this traditional energy-based model. And then we start by adding some isotropic Gaussian noise to this clean image X to get a noisy version X tilde. And then we define a conditional distribution of this clean image X given this X tilde. So this distribution can be derived as this formulation. So this formulation is derived based on the assumption that P theta X is given by this energy-based model, and X tilde is given by X plus sigma times ipsum, where ipsum is just like the standard Gaussian distribution. Okay, and comparing this conditional distribution with this marginal distribution, so the only difference is like it has this quadratic term, right? And when this noise scale sigma is small, so this quadratic term has the effect to constrain the energy landscape to be localized around the noise samples x tilde, so that the energy landscape would become less multimodal and the sampling could become easier, especially if we initialize the sampling from the x tilde. And that is the main idea of this work. And so to be more specific, so with the conditional energy-based model, as we just discussed, we switch from maximizing the marginal likelihood to this recovery likelihood function. So we name it recovery likelihood because it seems like it is trying to recover from the noisy samples to the clean samples. And we define the recovery log likelihood function as the average log conditional probabilities. Very simple. And to maximize this J theta, we would follow the same learning gradients as the regular maximum likelihood estimation to update the model. And the only difference is like for sampling, we instead of sampling do the sampling from the marginal distribution, we run longitudinal dynamic sampling from the conditional distribution, which is initialized from this x tilde. And more importantly, we theoretically show that maximizing this recovery likelihood function gives a consistent estimator of the parameter theta in the marginal distribution. Okay, so to further equip our model with the ability of generating new samples from like pure white noise signal, we propose to further learn a sequence of energy-based models on data perturbed by a Gaussian diffusion process. So this is also inspired by the recent denoising diffusion models. So specifically, given a clean image x0, we first repeatedly add isotropic Gaussian noise to the image until it degrades to a purely white noise image. And then we define an energy-based model at each noise level or at each diffusion time step. And then each energy-based model is trained with the recovery likelihood on adjacent steps, which maximize the conditional probability of the data at a certain noise level, given their noisy versions at a higher noise level. Okay, and after training, we can generate images by the sampling process that initializes from Gaussian white noise images and progressively samples the conditional distributions or marginal distributions at decreasingly lower noise levels until it reaches the clean image. And in terms of the parameterization of the energy-based models, we apply the similar idea as the denoising diffusion models, where we use this time step conditional network to parameterize the energy-based models at all time steps. To be more specific, for time step t, we assume this p theta x t is given by exponential fxt t divided by another normalizing constant. So this f theta would take the input x and the time step t as inputs, so that it could, like, we make the energy-based models at all time steps to share weights with each other. Okay, and we can also draw a connection to the denoising diffusion models or the score-based generative models, which are very popular recently. To be more specific, so recall this is the conditional probability defined by our energy-based models. And if we assume like the noise scale added to the clean image or the added to the current noise level is really small, so the sigma is really small, then we can do a Taylor expansion of this conditional distribution. And then we can derive that this conditional distribution can be approximatively expressed as a Gaussian distribution, where the mean of this Gaussian distribution is this x tilde plus sigma square times the gradient of this f. Sometimes people also call this as a score function of this probability, and the variance is this sigma square. So if we choose to directly parameterize this score function by a deep neural network, then maximizing the recovery likelihoods is equivalent to maximize the following training objective, which is exactly the training objective used by denoising diffusion models or score-based generative models. Okay. And this is a 2D toy example of our training algorithm, where we assume like the observed data is on a checkerboard in the two-dimensional data space. And the top row shows the progressively generated samples along the 6 diffusion time steps. And the bottom row shows the estimated density, marginal density at each time step. So it is worthwhile to mention that although we learn the models by maximizing the log conditional probabilities, we can still end up with accurate marginal density estimations at each time step, at least in this 2D toy example. And this shows the generation process learned on a category in the Alson Sing dataset. And it is worthwhile to mention that for our method, we could use like much less time steps than the denoising diffusion models, as small as 6 steps. Okay, and using this approach, we can achieve high fidelity image generation on various image datasets, including the Alson dataset, CIFAR10 dataset, and Celebrate dataset. And on CIFAR10 dataset, we obtain an IFID score of 9.60, which is a commonly used evaluation metric for sample quality. And this is competitive with a majority of GAN-based or like autoregressive-based models. And we further show that we can apply our learned model for a smooth image interpolation by interpolate between the noises added at each sampling step. And our model is also capable of image inpainting by just run the sampling on those occluded regions and keep the observed regions unchanged. So that is the task I mentioned at the very beginning. That is, we can do those like image editing tasks without retraining the model, but just run the sampling as like our target. And more interestingly, we conduct long-range chain analysis on the model with 1,000 diffusion time steps and observe that the learned models form steady long-range sampling chains. Recall that I mentioned this is a very big issue of learning energy-based models. And so to be more specific, so here are the 2 panels of samples generated from our model and generated from a baseline model. So this model is learned by short-run MCMC techniques and learn the marginal distribution P of X directly. So this 2 panels shows the samples with short-run MCMC chains. That is, we only run 100 sampling steps after training. And you can see like both panels look fine. However, if we run really long-range chains, for example, 100,000 sampling steps, so we could still get like realistic samples. However, for the baseline methods, it becomes really oversaturated, meaning like the learned energy potentials are still not feasible for the baseline methods. And with the steady long-range chains, we are able to estimate the normalizing constant or the partition function d theta by a newly important sampling, so that we can use the learned energy-based models for likelihood estimation on testing dataset. So the left figure shows the learning curve of this d theta with different number of sampling steps, and you can see with different configurations, the z would converge to the same value with large amount of samples. And the right table shows the testing bit per dimension, which is the likelihood estimation results on the testing set of CIFAR10. And our model can achieve like a reasonable likelihood estimation results although it still has a gap with the autoregressive based models. Oh, any question for this first part? Okay, yeah, I'll now move to the second method. The second method is called flow contrastive estimation. So for this method, I'm mainly curious about a question that is, can we completely get rid of MCMC sampling when training the energy-based models? So to answer this question, I will first do some prerequisite introduction. That is another type of generative models called flow-based models. So this type of models would transform a simple distribution in the latent space, for example, a factorial Gaussian distribution, to complex distribution in the structured data space by composing a sequence of invertible transformations so that the log probability in the data space equals to the log probability in the latent space, which is usually in a closed form because we assume the distribution in the latent space is really simple, plus the log determinant of the Jacobian. And this type of model, the key idea is like the sequence of invertible transformations will be carefully designed so that this term, the log determinant of Jacobian, would be easy to compute, so that this type of models would enable efficient sampling while this one-shot process, and meanwhile it also has this efficient density evaluation. Okay. So if we compare this flow-based model with the energy-based models, so the flow-based models are capable of direct generation and trackable density estimation, which are sorely lacking in the energy-based models. However, the flow-based models make strong assumptions that the transformations from the latent space to the data space are invertible, and they are in specifically designed forms, which may be highly constrained. And in contrast, the energy-based model don't make such assumptions and can be more flexible in form. Recall that we know that the F theta could be almost free form, right? So that the energy-based model may capture the modes of the data distribution more accurately than the flow-based model. So a natural question is like whether we could design a joint training algorithm for these two types of models so that we can combine the best of two worlds. That is to combine the trackability of the flow-based models and the flexibility of the energy-based models. Okay, so that is the main motivation. So to do that, so our work is inspired by this noise contrastive estimation work, which is proposed in 2010. So the basic idea is as follows. So recall this is the formulation of an energy-based model. So instead of estimating this d theta, so can we learn it as a free parameter instead of computing it? So that is the basic idea of this NCE. So we basically turn this log d theta as a free parameter that we would learn along with this f theta x as our model. But for this model, we definitely cannot train it by directly applying the maximum likelihood estimation, because for maximum likelihood estimation, we can simply learn this C to be arbitrarily small so that the likelihood could be arbitrarily large, right? So the idea of NCE is like we can introduce a noise distribution QX, and then we turn the estimation of an energy-based model P theta x or any type of unnormalized density function. We turn the estimation of this model into a classification problem. That is, we let this P theta x, which is our target distribution, to classify the real data from the data distribution and the data generated by this noise model QX. Okay, so in that case, we can theoretically prove that we can get a consistent estimator of the parameters of this P theta x. Okay, so seems like this is an appealing method for estimating entry-based models. However, there's no free lunch. So to make this algorithm work, there are three very strong requirements of this noise distribution QX. First, this QX must have an explicit normalized density function so that we can compute the value of QX in this training objective. Second, it should be easy to sample from because we need to draw samples to estimate this expectation term. And third, most important thing, this QX should already be close to the data distribution to make this algorithm be efficient enough. So in the original NCE, like they just proposed to use Gaussian distribution or mixture of Gaussian as this QX, which could be far away from the data distribution on, say, an image data set. So can we improve the original noise contrastive estimation method? So our idea here is pretty simple. We use the flow model to transform a simple and weak noise distribution to a more complex and stronger noise distribution that could be closer to the data distribution. So why do we use the flow-based model to do the transformation? Because it perfectly satisfies all the three requirements. First, it could be easy to compute the likelihood because of the careful design transformations. And second, it is easy to sample from the flow transformation via this one-shot like generation process. And more importantly, the flow model can transform the simple distribution in the latent space to a distribution that could be close to the data distribution. And in practice, we find that if we simply use a pre-trained flow-based model, it may not be strong enough to serve as the contrast of the entry-based model. So to this end, we also let the flow-based model to be adaptively updated through the training process so that it could be adaptively adjusted to become a stronger contrast. Okay, so in summary, our joint training algorithm is as follows. So the entry-based model and the flow-based model are iteratively updated based on a shared adversarial value function as follows. So if we look at this like a training objective from the perspective of entry-based model, it is just like a noise contrastive estimation with an adaptively adjusted noise distribution Q. And if we look at this training objective from the perspective of this Q, which is the flow-based model, it is approximately minimizing the Jensen-Shannon divergence between this Q alpha, which is the probability distribution of modeled by the flow-based model, and the data distribution. And if we expand this Jensen-Shannon divergence, it consists of two terms, which amounts to a weighted forward KL for Q alpha and a weighted reverse KL for this Q alpha. So we know that the forward KL usually amounts to the mode covering behavior, and the reverse KL usually amounts to the mode chasing behavior. So compared to the original maximum likelihood training of the flow-based model, which is mainly mode covering, so this Jensen-Shannon divergence is a mixed behavior of mode covering and mode chasing. So this helps to correct the over-dispersion issue of the MLE training of the flow-based model. Okay, so we can also, you might also already notice that our training objective, so this value function, seems to be quite similar to the training objective of a regular GAN-based method. And indeed, our method has a close connection to the GAN-based method in the following sense. So recall that this is the training objective of a GAN-based model. So here, this D is the discriminator, while this G is the generator, and the value function is just trying to, so the discriminator is trying to mislead the the discriminator is trying to classify the real samples and the samples from the generator, while the generator is trying to fool the discriminator. So here, the discriminator of the GAN-based method is like trying to, it is learning a probability ratio, which is this P data over P data plus PG. So this PG is the implicit probabilistic distribution like generated by this generator model. Well, in our method, this likelihood ratio dx is parameterized by two explicit probabilistic distributions, which is this P and Q. So P is the energy-based model, while Q is the flow-based model. So the advantage of this parameterization is like this. So suppose in the perfect scenario where this generator, the distribution of this generator perfectly matches the data distribution. In that case, if we in this GAN framework, this discriminator would end up with a random guess, right? But in our framework, this PX must contain all the learned knowledge in the Q in addition to the difference between data and Q. So in the end, if the algorithm perfectly converges, we would learn two explicit probabilistic distributions P and Q, and both of them would be close to the data distribution. Okay, so that is the key difference of our method with the GAN-based method. Okay, so this shows the training process of our method on some 2D toy examples. So the top left figure shows the target data distribution, and the top right figure shows the learned flow-based model, and the bottom left figure shows the samples from the flow-based model, and the bottom right figure shows the learned energy-based models. So you can see that compared to the flow-based model, the energy-based model is more expressive and can model the data distribution with discrete modes more accurately. And it is worthwhile to mention that the energy-based model we use in these 2D toy experiments have a much simpler network structure compared to the flow-based model. So our EBM only consists of three layers of fully connected layers, while the flow has to compose 30 invertible transformation layers. So that is that further verifies the fact that the EBM is more expressive because of the free-form energy function. And we also compare our training algorithm with the original noise contrastive estimation. So we can see that our method converges much faster in this 2D case because we use a stronger noise distribution, which is the flow-based model. And we also showed that our model is capable of generating high fidelity samples, and it can generate much better samples. It can also generate much better samples from the flow-based model compared to the original MLE training of the flow-based model. And it also leads to better testing log likelihood on various data sets compared to the flow-based model. And because like in this work, our energy-based model is already trained in a discriminative way, so we can easily adapt this training algorithm to a semi-supervised learning setting in the following sense. So suppose we have some labeled data belonging to K categories, and we have a large amount of unlabeled data. Then for the data in each category, we assume it is modeled by an energy-based model, P of K. And for unlabeled data, so if we assume that the labels are uniformly distributed, then the distribution of the unlabeled data, this P of X, could be expressed as the average of the PKX, which are the class conditional energy-based models over all classes. And recall that we have this correspondence between the energy-based model and the commonly used softmax classifier, right? Then we can make a small tweak of our original training objective of this flow contrastive estimation by adding an extra term. So this term is only for label data. And for label data, we use this correspondence to get the probability of the ground truth label Y given the input X. Right, so we use this correspondence to get this probability, and then we add this probability to our training objective. And this term is only used when we learn the energy-based model, not for updating the flow-based model. Okay. So with this small tweak, we first verify it on a 2D toy example. So in this 2D example, the training data consists of two twisting spirals. And these two twisting spirals belongs to two different categories. And for each categories, we give the training algorithm seven label data and a large amount of unlabeled data. And then we just use this training objective to update the model. And this figure shows the training process. We can see that in the bottom two figures, those are the two cross-conditional energy-based models. We can see that they end up with learn to accurate density estimation for each category. And we also have an accurate density estimation for the unconditional model, which is this P of X. So we can see that if we use this method to do semi-supervised learning, we are doing much more than just learn a classification boundary. So instead, we really learn the cross-conditional model distribution for each category, which are modeled by these cross-conditional energy-based models. And we also test the semi-supervised learning on like real image data sets. And on the SVHN data sets, we achieved the competitive results with some other specifically designed semi-supervised learning methods. And our method also outperformed the GAN-based methods by a large margin, partially because like for the GAN-based method, if you use the discriminator for representation learning or semi-supervised learning, the discriminator just learn the difference between the generator and the data distribution. In contrary, in our framework, the energy-based models learn all the information in the flow-based model, plus the difference between the flow-based model and the data distribution. Okay. I think this are all the contents I would like to cover in today's talk, and thank you for listening. And are there any questions?
Okay, let's all give Ruiqi a big virtual thank you. It'd be great to get questions. You can put them in the chat, or we're a small group. You can also just go ahead and unmute and directly ask a question if you have one. Xiaowei, do you have a question?
Yes, I do. So thanks for the presentation. I have a question regarding this energy-based model. So in the first part, in part of the issue to address MCMC, you propose the conditional probability distribution to that. So I wonder if you use conditional probability, would that lead to some issues related to mode collapse? So in such way that you are in a high dimensional space, you're going to be converged to only a finite number of nodes, unlike the general MCMC cases. So I don't know if you can comment on that. And that's my first question. And then second question, I wonder if you can say something about the comparing the energy-based model versus the scoring-based approaches in terms of the futures. What do you think about these two approaches?
Yeah. Those are really good questions. So for the first question, yeah. So I think, yeah, you're right. So if we really care about the conditional distribution, we learn from the conditional distribution. So it has a chance that, so for the other like regions, they might be remain unexplored, right? So that maybe it could be just like I mean, for example, if you just learn a single model, a single conditional model, starting from some noisy versions and try to recover the clean images, it might have a chance that those other reasons remain unexplored, so you can just only learn an accurate estimation around the clean samples. And this is also a commonly known issue for example, contrastive divergence training of NG-based models. But like in practical, we observe that because we have the weight sharing of the sequence of NG-based models across different time steps, this kind of have an implicit regularization of the NG-based models, so that even the NG-based function at, say, around the clean samples has some kind of accurate estimation around those regions with low density. It's just like, I mean, it's not like a explicitly analyzed effect, but it somehow has a regularization effect because of the weight sharing mechanism. Yeah. And as to your second question, yeah, so I think definitely the score-based generative models are very appealing method, and somehow you could treat it as a it kind of like learn the sampling process of the NG-based model, but instead it directly parameterizes the score function instead of the explicit NG function. I think this is the main difference. And for the score-based model, people have shown that it could lead to very strong like generation or like do some image-to-image translation, but somehow it still fails to extract very meaningful features or like for some representation learning purpose, because it is defined by a unit architecture, and somehow it doesn't really learn the feature itself. It just like learn the iterative sampling process. So I would say like the score-based model might be more useful for some like image editing or video editing tasks, while the NG-based model might be more promising in some feature learning or representation learning tasks. That is my opinion.
Mm-hmm. Okay, great. Thank you.
Mm-hmm.
So there's a question in the chat about what was the algebraic form of the energy function that you used in the image experiments. Was it a MLP of some image-friendly architecture, or kind of what is a good architecture to use? So
yeah. So for image generation purpose, we just use some residual network, but on the very top layer, we just don't have the softmax head. We just output a single scalar. And for the semi-supervised learning, for example, we need like class conditional EBM. We just learn like multiple heads, very much like a classifier structure, where for different class, we have different heads at the very top layer. Yeah. I think the advantage is like we really can use any existing well-explored classifier architecture for defining the NG-based models, so that we can really utilize the experience in discriminative learning for parameterizing the edge-based models.
Great.
So a quick question, as someone who hasn't done a lot of work in this space, just curious, if you look at like the function that the energy, like whatever the energy function is computing, and say if you use like the last layer of that function before you turn into a scalar, like for example, is there any interesting application of that? Have you looked at that? Like, is that something useful?
Oh, right. I think there's some work trying to extract features from the NG-based models, either from the very top layer or from like multi layers in the model, and they use the features to do representation learning, very much like what the most self-supervised learning methods did. Yeah, and they have shown that they could be promising in terms of representation learning. But yeah, I do believe there's still some more interesting things remain unexplored in terms of the learn features in the NG-based models. Then one thing people also have tried to explore is to do the compositionality. That is, we we can compose like separate concepts modeled by different entry-based models together, and yeah, do some interesting compositional generation.
Cool, thanks.
Any other questions? Okay, well, let's thank Ruiqi again for a great and very interesting talk.
Yeah, thank you.
And there's no seminar next week due to the President's Day holiday, but we'll be back in 2 weeks with another great talk. Thanks, everyone.